And I hope everybody has access to the videos on YouTube, right? And I see that some of you are listening. And what is really interesting is that sometimes I look and there's more than the people in this class listening. There's more than 5 people listening. There's 6 or 7, and I don't know where these are people in dire need of education, I suppose. So we're developing a following of at least one.
Well,
Okay.
some of us may have to watch it multiple times.
Oh, is that right? Oh, it's because I talk so fast. Okay.
No, just some of us need help.
Okay. Okay. Well, we're getting started late because the batteries in my microphone died. And I should quit saying that. I used to say that as a joke, and now I say it automatically. You know what a microphone is, don't you? It's the phonetic pronunciation of microphone, I believe, a microphone. Or maybe it's the Irish definition or the Irish pronunciation. I'm not sure. Okay, well, let's go ahead and get started. Let's look at the homework, and I think we're going to do the homework today. And wrong spreadsheet, correct spreadsheet. Okay, let's do the following. Choose a causal PDF for negative x, and choose a causal PDF. That means it's equal to 0 for negative x, and plot the probability that x is greater than or equal to a. I guess I should share my screen if I'm going to be reading this, because nobody likes you to read equations or homework problems. Okay. And plot this thing, the probability that x is greater than a versus the expected value of x over a as a function of a, and verify Markov's inequality. So I am not a political person, but today we are going to choose Glauco as 1, Justin. No, Glauco, you're 0. I'm sorry, man. Okay, you're nothing. You're 0. Okay, Justin is 1, Theo is 2, Adam is 3, and Matthew, you're number 4. So I'm using today Donald Trump coins. Is that okay? Okay. And that's one Donald Trump coin. This is another one. The other one is colored nicely. But this is not a political statement. These are just simply coins. Okay.
Super Marks.
Yes.
You're using 2 coins and we are 5 persons.
Yes.
5 people.
So.
I don't know my binary numbers. Okay. 5. Let's see. 0, 1, 2, 3. Yeah, you're right. It only goes up that much. Okay. I will see if I have another Donald Trump coin. And yes, I do. I have other Donald Trump coin. Plus, I will use I'm not going to use a Donald Trump coin. I will use a coin from Australia. And the coin from Australia has a very nice picture of Queen Elizabeth. I don't know if you can see that. And this is a coin which is dated 1996. So it's as old as most of you are, right? Okay, here we go. I don't want to drop it on my pad. I guess I'll move my pad here. And I don't want to drop it either because it's going to make a loud noise. What to do, what to do, what to do. Oh, well, you'll hear a loud noise. Did you hear a loud noise? Okay, that was something. Okay, 1, 0, 0. What's that? 4. Matt, you're up.
All right.
Okay, I will allow you, I will quit sharing my screen and allow you to share your screen, and that's going to make everything good in the world. Okay, go ahead. Show us what you did on the Markov inequality.
All right, so I just chose a real basic PDF is this function, and the probability of x is greater than or equal to a ends up being this function. And so I plotted that here.
So you
And
chose
then
you chose a uniform. No, you chose a PDF that went up at 45 degrees. Is that right?
Down.
Down, that it went down 45 degrees. I see. Okay.
And then
And you didn't put the interval here. The interval is from what, 0 to 2?
Oh, yes. Sorry.
No, that's
Yep.
okay. It's 0 to 2 though, correct?
Yes.
Okay. From 0 to 2. Expected value of, okay, 2/3. Probably. Okay, good. Okay, so what'd you get?
Yeah.
So this is an interesting PDF. I mean, this is kind of one that's kind of made up. Okay, go ahead.
Yeah. So this verifies Markov's inequality because the probability of x is greater than or equal to a is always less than the expected value over a on the interval.
Okay. It's kind of perfect. That's the way we know that it's going to be for all things. But I think it's always interesting to see that. Did anybody else do something which was interesting?
I did it to where comparing each side of the inequality against each other and then plotting y equals x and showing that Markov's inequality is always below y equals x, signifying that of x of a is greater than.
Okay, why don't you show that, Justin? I'm not sure where you're coming from, but
All right, can you see this?
yes.
So I plotted each side of the inequality on its own axis and then plotted the y equals x line, and the fact that since the inequality is always below y equals x, that means that this part is always greater than this part, which is what Markov's inequality says.
So why do you think that line is an upper bound for all probability density functions? I think that's what you're assuming here, right?
The upper line is the bound that would tell you if this blue line were to cross the orange line, then that would tell you that the probability that x is greater than or equal to a is greater than e of x of a.
Okay, well, is this, let's see, does this assume a specific probability density function?
Yeah, I used exponential.
Use an exponential. Okay, fine. Okay, good. Okay, Markov's inequality. So you used...
like if the line was out here at this point, you would have e of x over a is equal to 0.3, but e of probability of x greater than or equal to a would be 0.4, which that would be like saying that Markov's equality is wrong, and the fact that never happens, going all the way out to 100.
Well, no, I guess I'm curious here because the probability that x is greater than or equal to a given an exponential is not a linear line, is it? I guess that's how all lines are. They're linear lines, but...
Yeah, but no, this is just, the line is just as like a tool. It's not like the exponential or anything. It's just using as a tool to help you visualize that e of x over a is always greater than probability of x greater than or equal to a.
Okay, and then in the next... Say
anywhere
again?
lower, let's say anywhere on the plot in this below the orange line means that e of x over a is greater than probability of x greater than or equal to a.
Oh, probability.
Any value that you select here that's below the line will give you a value smaller over here.
Well, where do you get that upper line as x is equal to y? Where do you get the 45-degree line from? I'm not seeing that.
Well, so we're wanting to verify Markov's inequality, and the inequality is stating that the probability of x is greater than, or probability of x greater than or equal to a is always less than or equal to the expected value divided by a.
Yes.
So I'm telling you that based on an exponential PDF, plotting the expected value divided by a and calculating the probability of x greater than or equal to a, I'm basically showing you that, you know, for whatever value E of X over A you get, or whatever value of A you plug in for, you'll always get a value bigger than.
But aren't you assuming here the probability that X is greater than or equal to A is equal to A?
No, I mean this Y equals.
I think the line that Justin has drawn there is not based off the random variable X. It's just the line of slope 1, which would be the equality in this inequality.
Yeah, that's what I'm trying to say.
Oh.
It's not really part of the calculation. It's just there to show you this is the line where they would be equal. And if it's above the line, then the Y axis would be greater than
okay, and then the second plot that you did was for what? For just the exponential, right?
The second plot is just the same thing, but showing you out farther over time, showing that it the probability, you know, doesn't ever go above 1, given no matter what value you select of A, but E of X over A would increase. So we're just showing you that, like, kind of zoomed in on the first plot, it from 0 to 1, it doesn't ever go above, doesn't ever go like above or to break the Markov's inequality, and then going out to a large number, it holds true there too.
And what's the blue line?
Blue line is I'm plotting E of X over A versus probability of X greater than or equal to A.
For what density function?
The exponential.
The exponential. Oh. Okay, well, I do see that. Okay, well, thank you. Thank you for that. Anybody else want to share? Gosh, I sound like I'm in kindergarten. Does anybody else want to share? Okay, if not, that's fine. Let's go back to the screen here then. And let's look at the next one. Let's do the same thing for the cumulative, or I'm sorry, for Chebyshev's inequality. We're going to use Chebyshev's inequality very soon to choose to prove the law of large numbers. Okay, I'm just going to put these in my hand here. Tails, tails, heads. Number 1 is, that was Justin. Okay, what? Just did something, Justin. So 1117, that's an imaginary person. 110 is crazy. 100, which is 4. Heck, Glauco, you do it. See, what I should have done is I should have gone 1. And then you would have thought it would be fair, but I would be cheating if I did that. Glauco, go ahead.
I cannot share my screen.
Why?
Because you are sharing, I think.
Okay, I see. Okay.
So I did the exponential, and here is Chebyshev's inequality. The blue line is the probability that this is too small.
No, we can see it. I can see it.
Sorry. Okay, now it's better. So we see that they both approach asymptotically the bottom of the graph, but the orange line is always bigger. So it's kind of
okay. This is the second one is Chebyshev.
The second one, yeah.
I see. The
first one is the same, the exponential too, but the Markov's inequality.
Okay, something to think about. Do you think that these two curves always asymptotically converge as A goes to infinity?
They both approach to 0, but in different magnitude. I mean.
Oh yeah, well, of course. But do you think that they always converge to 0, both of them?
I think so. I have numbers till 1,000, and they keep.
Well, let's go back. Let's go back to your plot. Let's go back to your plot. Yeah, let's look at the blue line, the probability that x is greater than or equal to a. What does that approach as a goes to infinity?
It approaches to 0.
It has to go to 0, right?
Yeah.
What about the second one? The expected value of x, which is a finite number, divided by a as a goes to infinity. What does that approach? In the top plot.
Oh,
yeah.
Goes to.
It goes to 0 also.
0. Yeah.
Yeah. So all of these plots should asymptotically go to 0 for Markovs. Let's go down and see if that's also true for Chebyshev.
Okay. The absolute value of x minus the expected value
is greater than a. Should that go to 0 as a gets to infinity?
Yes.
Yeah, because you're asking if something is greater than infinity, right?
Right.
And the probability something is greater than infinity is no good. The second one, the orange line, also goes to 0 because as a goes to infinity, that goes to 0 for a finite variance, right?
Right.
So both of these plots, your plots, it's kind of a sanity check. Both of these plots go to 0 asymptotically. So that's kind of cool. Okay, Glauco, thank you. Okay. Are you having fun yet? Hope so. Let's do the 10 by 10 histogram. Who hasn't gone yet? Adam, you probably didn't get very much done.
I have this one.
Okay, why don't you dazzle us then?
All right. All right. So here we go. Got the whole set of data up here. Normalize it by the sum to get the PDF here. Change that over into a CDF, and then I plotted it on these contour curves here. You can see how, you know, they always, well, and they follow the same as the coloration here. So they increase as you go to 1010. You see though the PDF is not always perfectly increasing, but the CDF is, as it must be.
Okay. The PDF, oh yes, okay, I did. Okay, never mind. I was thinking of a previous instantiation of this. So you guys check your numbers. Is this about what you got too? Okay, we see now, of course, in the lower right, it does asymptotically go to 1, right? As a cumulative distribution function does. Okay, that was kind of fun. Okay, did you do the conditional ones too? Let's do the conditional ones. Okay.
So we got this one here, got a much smaller set of numbers, same deal though, change it into the PDF, sum it into a CDF. Similar looking plots, just smaller. Again, kind of just approaching a point on both of them.
Okay, great. Okay, thank you very much. What about the x is greater than a? Yeah, let's go greater than a.
Stair step, same deal, shape different.
Okay. Okay, everybody agree with those numbers? We all should have gotten the same numbers there.
I think the cumulative distribution function will be more populated in the upper diagonal, in that area, in that weight area. I think the cumulative distribution function will have repeated, the last number will be repeated in the line. That's what I have.
Well, that's if you want to consider cases outside of our bounds. But oh, is that something we'd want to do? Because yeah, it would just be drawing it across, I guess.
Yeah, but that's a good point. The cumulative the PDF is defined as you have it, but elsewhere the PDF is equal to 0. So if you wanted to, you know, for this, I don't think it's important. If you wanted to, all of that upper diagonal half could be labeled with a 1. Is that what you're saying, Glauco?
No, I'm okay with the probability with the PDF, but for the cumulative distribution function, I think that the white area should be populated because you can get, it's
Oh, yes, I'm sorry, I misspoke. It would not be populated by 1, but it would be populated by whatever the, I don't know, what would it be
the last
populated
value,
by?
the last value in the line.
The last value in the line, okay.
Something like that.
That's what I have, yes.
Okay.
Yeah.
The whole thing is applicable. A lot of redundancy, and we should have a leveling off here, which I guess we get with the brown to the right.
Yeah, you can see along the diagonal here, it just becomes constant going up then.
Yeah. Okay, good. Any questions on this at all? Okay, great. Thank you. Thank you very much. Well, that's pretty good for a sick guy. That's pretty good. Okay, and I guess that's all. That was a really simple homework problem because we said that we weren't going to assign 4. I'll be moving that in a while. So let's, any questions on the homework? Any outstanding issues? Okay. So last time we were talking about taking 2 random variables and compressing the joint probability density function into a probability density function of the 2 random variables. We went through the sum, that was the convolution. We went through the product of the random variables, and I think this was the general result that we got on the bottom. Not a pretty result, but this is what we get, as you can see in the upper right here, when we multiply x times y. And this is only applicable for random variables, all of whose probability mass lies in the first quadrant. And then we went through the example of, what was this, a uniform random variable, and showed that when you multiply the 2 random variables that you got a minus logarithm. And the minus logarithm is what you can see here in the, where'd it go? Yeah, the minus logarithm. And we talked about this, and it was kind of curious that this logarithm went to infinity, but that's kind of cool. That's kind of cool. So what we're going to do today is we're going to do the quotient, and this is going to be done in a little bit different fashion. The quotient is going to be due in a little bit different fashion. We're going to have the probability of a random variable x divided by a random variable y. Random variable x divided by a random variable y. Now we could approach this using the same technique that we did last time, or we could approach it a different way. We're going to choose to approach it a different way. Many of these problems can be worked in more than one application. And we are going to appeal to the scaling background that if y, capital Y, the random variable y is equal to a times x, you recall the scaling theorem that as if we multiply a random variable, what do? We take the probability density function and we stretch it out by a factor of a. But then again, to maintain the area of 1, we have to pound it down so that the total area is equal to 1. So this is the stretched out portion. This is the stretched out portion. And this is the pounding down value that gives it a value of 1. The overall area is equal to 1. Now, what we're going to do is we're going to pretend that A is equal to X. And we're going to assume that this is f of y given X. Now, this is confusing notation, so let me skip over it. Let me skip over it here, because what we're going to do is we're going to set A is equal to 1 over y. And we're going to assume with the probability density function that we are given A, or we are given 1 over y. And so here is the result. This is the result of the scaling theorem. We are given y, We are given y, and then we treat y just like a scaling variable here as a. So this is equal to y times f of x of yz given y, given y. So all of these are conditional probabilities. We are assuming that the random variable y is given, and then we are applying the conditional probability just exactly like it is a constant that we don't, that it's a constant. And we can do that because of the conditional probability. I hope that makes sense. So here is a restatement of the same problem. This is the conditional density function for this. And then what we'd like to do is we would like to look at the joint probability. Notice we have this. We have f sub z of z given y, but we would like just the density function for z, not given y, but would like the density function for z. So what we're going to do is we're going to take this conditional density function and we are going to multiply it out into a conditional into a non-conditional joint probability density function. What is this equal to? This is equal to the conditional density function times the density function in y. So this is just application of the idea of conditional probability. This is an idea of the conditional, just the definition of conventional a given probability if you're given a random variable. So that's what we want. So we're actually climbing uphill because we don't want the two-dimensional. We only want the one-dimensional. But this allows us to give the one-dimensional. This allows us to give the one-dimensional. And then how do you get from this joint probability density function to the conditional density function? Remember that you integrate out what you don't want. What don't we want here? We don't want this y. We want to get rid of the y. So we integrate out the y here of this density function. And this gives us, in the end, the probability density function that we would like. So this is, if you have z is equal to x over y, how do you get the density function of z from the joint probability density function of x and y? You substitute this equation that we have on the bottom here. So that's f sub z of z is equal to, and you can see the result here. So we did this very differently. We used the definition of conditional probabilities to arrive at our answer instead of dividing up the plane and integrating over the appropriate regions. So this is the example of the quotient of two random variables. Let's take an example. Here, just for our reference is the equation that we just derived. That if we have z is equal to x over y, the density function for z can be obtained from the joint density function of x and y using the equation that we have on top. That's what we've just derived. Now suppose that x and y are IID. Remember what IID means. It's independent and identically distributed exponential random variables, so that the joint density function can be written like this. Remember, just the one-dimensional random variable is e to the minus x. It has a density of e to the minus x times a unit step. So if we multiply this times the same thing with y, we get this joint, right? This is f sub x. And this is f sub y. And of course, we know that if we have independent random variables, the joint is the product of the marginals. The joint is the product of the marginals. So now what remains to be done is to take this expression and substitute it into this formula and simply evaluate the corresponding integral. And is that something we can do? Well, we can. It turns out that f sub z, if we substitute, as I had mentioned here, if we substitute like this is the integral that we want to evaluate. And this turns out to be a pretty easy integral to evaluate. I'm going to show you kind of an interesting way to evaluate that. If we integrate that with respect to y, and notice this is going to be what? Y z plus 1, right? So we have something that looks pretty easy to integrate, but I'm going to show you maybe an easier way to integrate this. And again, this is kind of old school. You can always go to Wolfram integral solver to solve it. But one of the ways to do it is to start out with the equation that we want and then compute the cumulative distribution function. Why do I want to generate the cumulative distribution function, which is the integral of this with respect to z? The reason that I want to do that, remember getting from here to here, this is equal to the integral from 0 to z of f sub z of some random variable, some dummy variable. And that's equal to the cumulative distribution function for z. And in performing this operation, what you do is you keep the value of y like it's a constant, and you just integrate with respect to z. The beautiful part of this is it gets rid of the y here. This is actually an integrating factor, if you remember back to calculus 1. And we get this integral. The cool part about this integral is this is easily integrated, much more easily integrated than the result, and then the result up here. You would probably, if you were going old school and you were doing this with pen and paper, you would probably use integration by parts. And you could do it. This is another way that doesn't use integration by parts. Rather, it uses I think, a more clever sort of approach. It manipulates it by an integral into something which is integrable. Then you integrate it. And then lo and behold, once you get the integral, you can differentiate again. And you generate the corresponding probability density function for z. So this goes through a little math, that's all. So all of this frame is to get from here down to here. And I went through what I think is some clever math, but you don't have to do that. You could integrate by parts, or you could look it up on the Wolfram integral number cruncher. So this is the density function for z. You'll notice it kind of looks like a Cauchy, but it is not a Cauchy. A Cauchy would be a 1 over, or a constant over z squared plus 1, right? That would be a Cauchy. But it does have the fat tails like the Cauchy, and we would expect that this would have an infinite second moment. So this is an example of the quotient of two random variables when both of the random variables are exponential. And just like the Cauchy, we get something which is not very friendly. The second moment here is equal to the integral from minus infinity to infinity of z over 1 plus z squared. Is that right? This is the second moment. We won't go through the first moment, but just the second moment. Is that okay? Now, no, that's wrong. That's wrong. What did I do wrong here? What should I put? Whoever answers gets a nice, what? Yeah, that's right. Oh, thank you for answering before I offered the prize. That's.
Oh, I mean, you were in the process of offering.
Okay. But here's the thing. This is the second moment, right? And I maintain that since the integrand is even, this is true. Do you agree? I'll write it down and see if you agree with that. Right? The integrand is even. Is everybody comfortable with this or not? I actually don't think that's right, come to think of it. Forget that. Because I can make my point without doing anything. The integrand is positive, correct? And what does this integrand approach as z goes to infinity? Yeah, Theo, I read your lips, Theo. It goes to 1, right? So we're asking for the integral over something that asymptotically goes to 1. That's going to be infinite, right? So the second moment here is going to be infinite. And so we have the same problem as we did with the Cauchy. Sorry about that. I'm embarrassed about that. That is not an even function. It's an interesting function, but it is not an even function. Okay, so you do things with innocent appearing random variables with a finite mean and a finite variance, and you combine them, and sometimes you get stuff with an infinite second moment, which is what we had here. Let's talk about expectation. We know how to do expected values. We're going to do expected values of higher dimensional random variables. And we are going to show that there are 2 ways to find the expected value of z. The idea is that z is equal to g of x. The hard way to do this is to find the dense, well, I'll go through the hard way in a second. The easy way is just to perform this integration. Expected values are expected values, and it's hard to mess them up. So this would be the smart way, is just to evaluate this integral. The dumb way, which is very slow, is to give this random variable transformation, compute the density function of z, and then integrate it out like this, right? So you can take this result, you can compute the density function of z, and then use that density function of z to find the result in a more conventional expectation. This is the dumb way to do it in general. Why? Because you don't need to know f sub z. The only thing you need to know is z. Why compute the density function if you don't need to compute the density function? Why compute the density function if you don't need to compute the density function? Up here, we don't have to compute the density function of z, do we? The smart way. We simply compute the expected value of z by substituting into the integral, the multidimensional integral. Now, these look to be different in some sense, but they're going to give you the same result. They will give you the same exact result. One way, very, very simple. The other way, very, very difficult. Okay, I need a timekeeper. I don't have access to a watch. So I want somebody when it's 5 minutes before the end of the class to hold up 5 fingers. And you can all do it, and that'll give me an idea of when to wrap up. Unfortunately, I don't have a clock, which is really accessible here. I need to do that. Okay, so this is expectation. Again, the dumb way and the smart way. Let me give you an example. The example here is, suppose that I have X and Y uniform on 0, 1. So therefore, the two-dimensional probability density function kind of looks like this. It's equal to 1 inside the square, and it's equal to 0 outside the square. So it's a little pillbox existing on the XY plane. And we want to find out what happens when Z is equal to the cosine of 2 pi X plus Y. Does that make sense? The dumb way is to figure out F. I can't even spell dumb. The dumb way is to figure out F sub Z of Z. In other words, find out do the transformation of the random variable here. And then from that, evaluate the expected value of Z, right? But again, the only thing I'm after here is the expected value of Z. There's no reason that I need this entire density function. I can rather integrate over the density function. This is F sub X of Y. And notice that the joint density function is just non-zero over the interval from 0 to 1, right? So I'm going to integrate over that interval from 0 to 1, 0 to 1, and over that interval, the density function is equal to 1 times the cosine of 2 pi X plus Y. Is that okay? And integrate it over dx and dy. This is a simple integral, and it turns out to be 0. In fact, you can kind of look at it. Let's see if I can do this. I'm treading in dangerous area now. If you look at the cosine, what's the value at, let's see, X sub Y is equal to 0. What's the value here? We're just going to look at the cosine of 2 pi X plus Y. What's the value here? The value here is going to be 1, right? What's the value here when both are equal to 1? What's the cosine of 4 pi? One. And right here along this line is we have the integral. This is also 1 along this value of 2 pi. And then we have it dipping negative. We also have positive and negative values. Anyway, it isn't apparent from my off-the-cuff analysis, but the total area here is equal to 0. So it's much more easy. My point is, this is much more easy to evaluate this cosine than it is to do it the dumb way and compute the density function of Z and then compute the expected value of Z.
Dr. Marks?
Yeah.
What'd you write there in front of the cosine? Is that supposed to be a 1 because it's uniform?
You mean here?
No, on the equation of E of Z.
Oh, this is along the line. Oh, come to think of it, that's probably wrong. This is on the line y is equal to 1 minus x, right?
Yeah, I was on the equation that's written out on the slide. You have the integral of y equals 0 to 1.
Yes. Oh, I just put in here the value of the PDF, which is 1.
That's what I was thinking. Yeah.
Yeah, this is the value of the PDF, which is 1 in that interval. Does that answer your question?
Yeah, that's what I was thinking it was.
Okay, yeah, sorry. Sorry, I don't have the world's best penmanship. So again, that's the smart way to do expectation. Almost always, there's always exceptions, but it's easier to do it that way. Now, if X and Y are discrete random variables, we can use the probability mass functions to compute expected values. It's a straightforward generalization of the one-dimensional counterpart. And it's just the summation of G, just the summation of G times the probability mass functions. Now, just like in one dimension, we have moments. Remember the nth moment of the probability density function was equal to the expected value of x to the n. Well, now we have two variables. We have an x and we have a y. So we refer to the joint moments of the probability density function as the expected value of x to the L times y to the k. And that gives us the nth moments, if you will. And if L, what if L and K are equal to 0? What's this equal to? Let's do a little bit of sanity checking here. If both L and K are equal to 0, what's that integral equal to?
1.
Yeah, it's equal to 1, right? Because it's just the area under the joint density function. Okay. And then you get x sub, if L is equal to 1 and y is equal, what happens if L is equal to 1 and y is equal to 0? If L is equal to 1, you get this. Do you agree with that? Which is equal to, I'm sorry, this should be x to the 1. Well, let's do that. Let's just do that in general. Let's do L is equal to something, but K is equal to 0. So we get x sub L and the K is equal to 0. So that goes to 1, correct? And then we are left with the integral of x to the L. And we're just going to do the integration over y here. And I'm running out of space. What is this equal to? This should be a dy over here to the right. What happens if you integrate out the variable you don't want in a joint? You get the marginal, right? So what is left is nothing more than the density function. Well, we get x to the L. And what we get then is just the density function for x. Interesting result. So this is nothing more than the Lth moment of the random variable. So we can get the one-dimensional moments from the two-dimensional random moments by playing around with stuff. Okay, I'm going to ask you a question. I'm going to see if your intuition is working here. Suppose that we have a density function. I'm going to kind of draw the contours of the density function, and I'm going to draw it kind of cattywampus so that it's not symmetric at all. The mean of this two-dimensional random variable is the point where if I cut this density function out of wood, and so I had a contour out of wood, it would be the point where it balanced. In other words, if I cut this thing out of wood, it would be the point where this density function balanced. Remember, we saw that kind of in 2 dimensions also, correct? Where do you think that balance is at, that 2-dimensional probability density function? It has to do with the moments.
I guess it'd be like the intersection of the moments, wouldn't it?
It would. Yes, in fact, that's exactly right. here's kind of Adam is correct, totally right. This is here's kind of a more elaborate explanation. If I had a two-dimensional surface, should I be able to, in theory, balance it on a string as opposed to a point? I should be able to balance it on a string in some fashion, correct? If I balanced it on a string and I wanted the string to go this way, that string would be balanced at x bar, which is the one-dimensional mean of that probability density function. What about if I wanted to balance this on a string going this way? That would be on y, or the mean of y. So you can think of the point of balance as being on a string, and then there's a place on the two strings, both of which balance it. And that's where the strings intersect, as Adam said. And that then is the point of balance that you have on your two-dimensional probability density function. So that's a good physical way to think of it. Okay, what else is going on here? Down in the bottom here, we have the probability density function for, a probability mass function. And this probability mass function has discrete points on the probability plane, and you generate the joint moments as is shown here. You generate the moments as is shown here. So let's go to the next slide and see what is happening. Okay, here we get to some important moments. The first one is the correlation of X and Y. Do you remember we said that correlation in the dictionary kind of is a synonym for independent? You remember that? Well, we're going to look at this generation, or the generalization of this. If the correlation is equal to 0, X and Y are said to be orthogonal or equivalently uncorrelated, right? So if this is equal to 0, then they are orthogonal or equivalently uncorrelated. Does that make sense? Now, here's what's interesting. If X and Y are 0 mean, if, let's see, if X and Y I'm sorry. This is not uncorrelated. This is still orthogonal. But let me just point out, if X bar is equal to 0 or Y bar is equal to 0 and they're independent, I'm just going to skip that because I accidentally erased it. It was a good thing that I did. Let's talk about the covariance and just skip ahead to the covariance. The covariance of X and Y is given by this expression. You'll notice that the variance is a special case if X is equal to Y. In other words, it's equal to the variance. Man, what am I doing? Okay, this is equal to 0. No, it isn't. It's equal to the variance if X is equal to Y. That's what I want, right? So if X is equal to Y, it's equal to the variance. You've seen that definition of the variance, I hope. And so this is a generalization of the idea of the variance. It's called the covariance. So this is the covariance of X and Y. And you'll notice up here, and this is where I got screwed up before, if X is equal to Y, then this is equivalent to the second moment, right? The correlation is equal to the second moment. So this is the covariance. If you work out the math, it's the covariance is equal to this. It's a generalization of the variance. And then we define something called the correlation coefficient. If you've ever had statistics, you know about the correlation coefficient between two random variables. The correlation coefficient is equal to the covariance divided by the standard deviations in X and Y. These are just definitions. These are just definitions. And we can simplify this to the following. We can simplify this to this result. How do you know that? Because X minus X bar times Y minus Y bar if we are to take the expected value of this, this is equal to the expected value of X times Y. And then just we do the cross sort of stuff, right? X times Y minus X times the expected value of Y minus Y times the expected value of X plus X bar Y bar. So expected value is a linear operation. So we can write this as separate things. So we get X bar, Y bar. Minus, before I go on, let me ask you this. What's the expected value of 3? That's right, it's equal to 3. It's equal to 3 because this is equal to the integral of 3 times the density function for whatever random variable you're looking at. The 3 factors outside, and we get the integral over the density function, which is 1. Yeah, so the expected value of a constant is equal to a constant. So here we're going to have, the next thing is we're going to have the expected value of X times Y bar, and we're going to use this idea in a little bit, minus Y X bar plus X bar, Y bar. Now we have to remember that these X bars and Y bars, these first moments are numbers. They're nothing more than numbers, right? They're not random variables anymore. They are the center of masses of the probability density function. So what we have here is XY minus, this is a constant. So we can factor it outside. This is a constant, so we can factor it outside. This is a number, and so the expected value of a number is that number. And so you can see what we have then. It's the expected value here. And then we have 3 terms, which are all exactly the same. We have X bar, Y bar. We have 1 positive and 2 negatives. So this turns out to be minus X bar, Y bar. Turns out to be X bar, Y bar. So this is exactly what is in the numerator here, and is how we got from the covariance down to this expression. So I've just derived the last step here. Any questions on that? So this is the correlation, just giving you definitions here, the covariance and the correlation coefficient. one can show the correlation coefficient is bounded. Do you know what the correlation coefficient goes between? From your old statistics class? If it's 100% related, the correlation coefficient should be 1, right? If the data goes against itself exactly, it should be -1. So the correlation coefficient is always between -1 and 1. Yeah. 5? Oh, you think it goes up to 5?
No, we just crossed into the 5 minutes remaining.
Oh, 5. Oh, I see. Okay. Thank you.
Highly correlated.
Highly correlated. Okay. So this is good. Okay. Last 5 minutes. I'm going to hit you between the eyes with the joint Gaussian random variable. This is, man, this looks ugly, doesn't it? Lots of things in here. The joint Gaussian random variable has a bunch of things. It has a correlation coefficient. It has sigma 1. It has sigma 2. It has mean M1 and mean M2. And I guess that's it. So it has 1, 2, 3, 4, 5 different variables associated with it. And we know in one dimension, we have 2 variables, right? We have the mean and we have this, we have the variance. The mean tells where it's centered. The variance says how far it's spread apart. We can do a similar sort of interpretation here. And to do this, this is very interesting. If I have any function, and these are contours, and I do any function in the world, like suppose that I have contour functions. I have contour functions here, and along this contour, the function is equal to A. Is that okay? Along this contour, it's equal to A. Now I'm going to do E raised to the G power. I'm going to plot a new a new function. I maintain that the contours are exactly the same. Because here, what's the value here? The value here is going to be equal to E to the A. The value along the contours is very different, but the contours remain exactly the same. I think this is kind of cool. So if you have contours and you take that and you cube the function. So you have a function with contours and you cube the function or raise it to the E power or take the cosine of it. That original function has contours. If you take the cosine of it, it's going to have exactly the same contours, except the values on the contours are going to be different. Isn't that interesting? The answer is yes. So that's what this is trying to say. Any function of G is also going to have exactly the same contours except for f of A. It has the same contours, but the value on the contours are different. So here's the joint probability density function that we had. So the contours of this probability density function are exactly the same as, this is the only thing that's a function of X and Y. They're exactly the same as the contours of the thing in brackets that I've just denoted. It's going to be exactly the same. If you look at this and you remember back to analytic geometry, you remember that this is an equation of an ellipse. So the contours of the Gaussian are always ellipses, or special cases, a circle. So this has the same contours as this g of x, which is the argument in the brackets, and this is an equation for an ellipse. So we're going to have elliptical contours for the probability density function. And here's the way it goes. The density function looks like this. It looks like a gumdrop, and it looks like a gumdrop which is spread out. And it can be stretched in one dimension, it can be tilted. And here are the parameters. M1 is the center of mass. Remember I said that along this line, you could balance the density function? That's where you can balance the density function here. That's where you can balance the density function here. There's also a sigma x. Now, sigma x says how much this density function is spread out in the x direction. And we have a sigma y, and the sigma y tells us how much it's spread out in this direction. And then we have our little correlation coefficient, which is rho. And this rho tells us how much this ellipse is tilted. And I won't derive it, but the theta, the rotation of the ellipse, is given by 1/2 times this arctangent here, okay? So that is the rotation. So we see now all the function of each of the 5 parameters. M1 and M2 tell us where this ellipse is centered. Sigma x and sigma y tell us how much it's spread out. And the correlation coefficient, in a weird way, tells us how much this thing is tilted. So I want you to consider this for next time. The marginals are one-dimensional Gaussian random variables, so that if I were to take this two-dimensional random variable, I guess I can go to the other side. No, I don't want to go to the other side because the list is on the bottom. If I were to take the projection of this, remember you project out the y-axis, and I was just going to get the probability density function for x, it would be a Gaussian. If I projected it this way, it would be a Gaussian. And guess what? Guess what the parameters of those Gaussians would be? M2 and sigma y, M1 and sigma x. Those would be the parameters of those Gaussians that are the projection, which you get by integrating out the variable that you don't want. When do the Well, we'll consider this next time. I want you to consider this, and I'll see if you can get this. Do Gaussian marginals imply a joint Gaussian random variable? Can you come up with a case where you have a random variable which has Gaussian marginals, but does not have a Gaussian joint? Anybody hazard a guess? This is just a little brain tickler. You think about that for next time. And then, when is the joint density function a line mass? In other words, when does this ellipse here, when did this ellipse basically collapse to a big long ellipse that if you pulled it out and kept pulling it out, it'd become a line mass, kind of a Dirac delta, if you will. I'll give you a hint. It has something to do with rho, okay? Okay, I think that's it. Are there any questions at all? We're covering some really good stuff, and I'll try to give you some, this, by the way, is just a heat map of what a Gaussian looks like. So I'll try to give you some interesting homework that we'll have due a week from today, and we can talk more about it then. Any questions at all? Okay, are you having fun yet? Okay, wow, no responses. Okay, nobody's having any fun. I'm having fun, so I hope you're having as much fun as I do. So we will talk to you very soon, okay? Last chance, bye-bye.